Hi everyone, thank you for coming to my presentation. So today I'm going to share with you my final project. So, and in this project, I'm using the DeepChem library to predict the protein ligand binding affinity. So the library I use is called DeepChem and it's licensed from MIT and it already has more than 5,000 stars. So it's a very, very popular library used for the use deep learning for the structure biology data. And okay, so we know that the drug development process takes long times. So every 10,000 compounds, only one of them will success to the last become a drug. So you can see 10,000 versus one. So it's very, very difficult to find the target drug. So currently there's a recent years there's a lot of application in help use the deep learning model to help to screen those compounds and find the better drugs. And in this project, I just want to do some introduce of how to use those the DCAM, this popular library for the for some drug discovery process that is finding the binding affinity between the compound and the target protein. So before using the DeepCam, of course, you need to install those packages. So you need to install the DeepCam and RedKit and also PDB fixer. The PDB is the input format for the data. And so as I mentioned earlier, DeepCam is very popular. It's open source using the deep learning in the drug discovery and also you can use it for the quantum mechanics and other biology predictions. And because we are using the molecular structure data and for both ligand and also the protein. So in order to process, to run the model, we need to just convert this structured data into the metrics. So the visualization or feature extraction is the terminology that we use. We are represent to convert the structured data, molecular structured data into metrics data. So the data set I use in this project is I use the protein ligand complex data set that is from the PDB bind and it's from the molecular net data set. In that data set, it contains uh, more than 4,800 protein ligand complex data. It's combined protein and ligand data. But for this project, I select roughly 100 from those data sets to run the model in order to save some time because the structured data takes time to processing. And also I do one more step. That is that the source code is from the DeepCam tutorial, one of the DeepCam tutorials. And when I run the first time when I run the model, I find that the uh, the accuracy is pretty low. And then when I dig into the data, I find that after I convert the ligand or protein into the matrix data, I saw some of them uh, have zero uh, entry in all the cells. So I just remove those data after conversion. It shows all zero. I remove those ligand and protein. Few of them. After I remove those data, and I get a very the accuracy is improved a lot. Okay, so this is the example data. This is the on the right hand side is the ligand and protein combined data, and on the right hand side is only the protein data. And I can show you the yeah, this is the structure data. So we want to predict the binding affinity between this the ligand is the compound and the target protein. So this is quite interesting, our project. Okay. So and the binding affinity, I don't need to explain the binding affinity. Binding affinity is very useful for the drug screening, and we have learned that in our homework 8. And so if you are interested, you can just Google what is the binding affinity. And in this project, particularly in this project, the source code use the random forest regressions. Basically, is the random forest is the machine learning model, and you can construct the decision tree, and combine with the regression, and just we used for the predictions, and we use the random forest regression and combine with the DCAM to the prediction. And our evaluation is we use the Pearson R square to measure the performance. And in this project, I have run 4 different type of model based on different input or uh, uh, different library. And the first model I run is I only use the ligand at data as input. Although we are predicting the ligand and the protein binding affinity, but here only the ligand, only input data is the ligand. We don't use protein data. And the ligand data and the input data is the SMILE data. So the ligand every compound you can write in the SMILE format is the alphabet just like the sequencing numbers. And the result is that in the training data set, the R square is pretty good. It's 94% of the accuracy. That is very good. And but in the when we run the testing data set, the R square dropped from 94 to 24. So it dropped a lot. It just suggests that some overfitting or something that just did not capture the binding affinity just from the model. And I think in the part of the reason is that it only have one, it only have the input for the compound, not the target protein. So that might be the problem. So in the second model, just I use the two input. I have the ligand input and also have the target protein as the input. But here the target protein dataset is original dataset also contain the ligand data is combined complex data set. And so uh, in the first model, we use the circular fingerprint for processing the data to convert the data set. But here since we have input, two structure input, we need to use the function that can accommodate with two input, two different structure input. So here I use the contact circular fingerprint as the convert functions. And the result is that for the training data set it's still very good, but for the testing data set is not that good. It's only 2% of the accuracy. That is so bad. So I think that the problem might because of that in the protein data set, you also contain the like ligand data inside. Okay, so in order to improve this model, so the first two model is from the tutorial. So the first is from the DeepCam tutorial. I just the is the first two model, and then the third model is I just write my own code for the third model, and I want to clean the protein and ligand complex data set. I want to just have the protein. So I find that there's a library called Bio3D. It can remove the ligand from the ligand and protein complex, the combined data set. And so I apply that library, but I get the very similar results. And then I take a look of the data set. I find that this Bio3D package did not remove the ligand from the ligand and the protein combined data sets. So that's why the reason that the prediction the predict the I got the same very poor prediction in the testing data set. That is, I apply the R package to do some data cleaning. And then since I figure out this problem, so I use the uh, bash command to remove those ligand data from the ligand and protein combined data set. And I get similar result in the training data set, but in the testing data set, it just the R square is still very low. It's only 14%. So okay, so that is my project. There's still some problem because since that is the model I think we should use in order to predict the binding affinity, we need to have both the ligand data and the protein data as the input, and I did that, and I used the DeepCam as the library to convert those structured data into the matrix data, and use some machine learning model to do the prediction. But somehow some of the important binding the mechanism of the binding affinity does not capture from the model. And so since I only have just 2 weeks to do this project, I don't have time to run all different model. But this is the definitely be the interesting uh, project. And yeah, at least I show you how what I'm sold and how to find the binding affinity based on the structural data set. And I have the in my Word document, I have the step by step very detailed uh, instruction to how to use this library, and also the source data set is from this okay. I think I put the source data. Yeah, I put the source data set here is from the tutorial part 13. And it is a very interesting project and learn a lot. And also I like to play with this 3Ds uh the structure software that is very interesting. But this this software only have the 30 days license for if or you after 30 days trial you need to purchase the license. Yeah. Okay, I think this is my presentation, so I want to stop here. And if you have any questions, please welcome to contact me. Thanks. Bye.